Fluorescence and phosphorescence are phenomena in which electron transition occurs and light is emitted. In both phenomena, electrons have various energy states and light is generated, but there are differences in electron transition process, light emission intensity, and time. Let's look detail about fluorescence and phosphorescence. Fluorescence is a phenomenon in which a molecule absorbs light energy and then emits it as lower energy light. Fluorescence begins with stimulated absorption. When molecules encounter light, they absorb its energy, elevating to an excited state. It's the initial step, where molecules absorb light and move to a higher energy level. In this excited state, molecules collide with surrounding ones, releasing energy without emitting light. This non-radiative energy release causes molecules to step down the ladder of vibrational levels, returning to a lower energy state. However, because the energy received by the surrounding molecule is not too large, the excited molecule cannot go down to the ground electron state. Therefore, this molecule stays in this excited state until it causes spontaneous emission, and then releases the remaining wild Mach-Sebastian energy as radiation. As molecules transition back to lower energy states, they undergo a downward electronic transition, following the Franck-Condon principle. The resulting fluorescence spectrum displays the vibrational structure of the lower electronic state. The bright orange or green colors of fluorescent dyes are examples of these effects that can be seen in everyday life. These dye molecules absorb light in the ultraviolet or blue region and then emit fluorescence in the visible region. Phosphorescence is a phenomenon in which an object emits light for an extended period after being exposed to light and even after the light source is removed, or the emitted light itself. Phosphorescence begins with the absorption of light energy, which excites electrons within a molecule, promoting them to higher energy levels. This initial stage involves the absorption of photons by the molecule, elevating it to an excited state. Following excitation, the molecule undergoes intersystem crossing, where the excited electrons change their spin states from the singlet, opposite spins, to the triplet, parallel spins, state. This process is relatively slower compared to fluorescence, causing a delay in the subsequent steps. In the triplet state resulting from intersystem crossing, the excited electrons possess a lower probability for decay. This leads to an extended lifetime of the excited state, allowing molecules to persist in this state for an extended period, ranging from milliseconds to hours. Eventually, the excited electrons transition back to the ground state by emitting light. However, this transition is relatively slower than in fluorescence due to the selection rules associated with the triplet state. This delayed emission characterizes phosphorescence. The emission of light occurs as the electrons move from the long-lived triplet state to the singlet ground state, emitting photons and displaying an afterglow or persistence, which distinguishes phosphorescence from fluorescence. As we saw earlier, there is a big difference between fluorescence and phosphorescence in the presence or absence of an intersystem crossing process in the process. Other than that, in fluorescence, spontaneous emission of radiation occurs within a few nanoseconds after the exciting radiation is extinguished. In phosphorescence, the spontaneous emission may persist for long periods. That is, fluorescence is a fast conversion of absorbed radiation into re-emitted energy, and that phosphorescence involves the storage of energy in a reservoir from which it slowly leaks. Let's learn about spectroscopic equipment that applies concepts that we've been dealing with so far. First, let's get to the rough structure. It can be divided into light source, which is the part that shoots light, wavelength selector, which is the part that selects light from the light source in detail or allows only the desired light to go out, sample part, and detector part, which detects light. Light that can be used as a light source includes X-rays, ultraviolet rays, visible rays, near-infrared rays, and infrared rays, mainly using xenon lamps that deal with light ranging from ultraviolet rays to visible rays, and hydrogen lamps and halogen lamps. Analysis using a spectrophotometer requires a monochromator that separates specific wavelengths among the various wavelengths of light from the light source because it is necessary to obtain transmittance to light of a single wavelength. A detector is a device that measures the intensity of light, and it functions to turn light into an electrical signal. The most commonly used type of detector is the photomultiplier tube. Using the principle of the photoelectric effect, it has electrodes for secondary electron supply called dinodes, so that the primary electrons generated from the anode receiving light pass through the dinodes and generate many secondary electrons. In other words, after one primary electron passes through 10 dinodes, about 100 secondary electrons are created. By amplifying the current in this way, even weak light can be effectively detected. Based on the structure of the spectroscopic equipment we have looked at so far, the principles of spectroscopic equipment are as follows. First, optical system exposes the sample by irradiating the sample with a specific wavelength. And then, excited samples emit light of different wavelengths. The wavelength emitted is collected by the second optical system, and the signal is measured by a light detector, such as PMT. In this video, we will mainly cover the most widely used fluorescence analysis equipment among spectroscopic equipment. Let's take a closer look at what fluorescence spectrophotometer analyzes. First, light from the light source passes through the first lens, and only UV and visible light passes, and visible light is absorbed by the excitation filter and only UV passes. The light is focused on the sample through the second lens. Some of this light is absorbed, some molecules are fluorescent. Fluorescence is emitted in all directions. Some of the fluorescence passes through a second filter or monochromator to reach the detector, which is usually placed at 90 degrees on incident light to minimize the risk of transmitted or reflected light reaching the detector. After UV is absorbed by passing through the emission filter in a 90-degree position, the visible light reaches the detector and the detector measures the fluorescence. So far, we've learned about each process of fluorescence and phosphorescence, its differences, and the spectrophotometer that analyzes substances using this principle. If this principle is well understood and applied, it can be used not only in life sciences, medicine, and pharmaceuticals, but also in industrial fields such as architecture and displays.